For each molecule, specify the polarity of the bonds and the overall polarity of the molecule. Okay, so let me write this down. And then have H bond OH. Okay, it's asking, I want to know the polarity of the bonds and the overall polarity. So let's look at polarity of the bonds first on this compound. So bonds and then the molecule. Bonds and the molecules. So it's polar or non-polar here. So we're looking at first this guy here, right? So we have, this is BeCl2, beryllium chloride. And what we're doing here is we're looking at the bonds first. So we're looking at specifically the beryllium and chlorine bond. You can visualize it as either this guy here or this guy here. Either one works. It doesn't really matter how you visualize this, but I'm going to redraw this as Be bond Cl. And if you look at these two compounds here, one beryllium exists on the kind of the left side of the periodic table, and chlorine exists on the other side of the periodic table, which means the electronegativity difference, as we know from our periodic trends, is going to increase as we go across a period. So, which means we know that these two compounds actually have a dipole. We know that this here, chlorine, is pulling electron density away from this beryllium, which means for the bond itself, it's actually, this here is polar. Because we have a polar bond between these two guys here, right? The dipole is pulling electron density away from this beryllium here. So this will result in a polar bond. Again, chlorine is much more electronegative than our beryllium here. And then in terms of our molecule though, if we look at our molecule, let me do this in red or something like that. The chlorine here is on both sides. So it's actually going to pull electron density this way and also this way. But this means that these dipoles actually cancel out, right? So I have a dipole moment going this way and it's going this way. So these two guys are going to cancel out, which means this molecule here is actually non-polar. So polar bond, but non-polar molecule here. And let's look at our, this here is H2O. Again, HOH here makes H2O. If we look at our bonds here, we have our oxygen bonded to our hydrogen. And then we have oxygen with these lone pairs here. As you can see, if you go back to your periodic table, hydrogen belongs here, oxygen belongs all here. Very, very big electronegativity difference. So the oxygen is going to pull electron density away from this hydrogen here, which means it results in a polar bond. And then for the molecule itself, if you look at this molecule, I have, again, oxygen is this negative charge here. It's going to, and the hydrogen has these partial positives here. It's actually going to pull away from this water molecule here. These lone pairs are actually going to shift the geometry. So it's actually not linear here. Water is actually drawn like this because these lone pairs want their space here. So in this case here, this guy is also a polar molecule because these electrons are moving away from this hydrogen. There's a net dipole pushing this way. There's the partial negative on water here. So this is also a polar molecule. So as you can see, polar, non-polar, which is good, and then polar and polar. So the solution here is correct.